Okay, so we can start.
Yeah.
Okay, thank you. Good afternoon, everybody. Thank you for joining. Today we have a IRSOL seminar presented by Professor Constantina Sigismondi, and little information about him. He is working at Sapienza University of Rome and is interested in secular variations of the solar diameter. In the last quarter of the century, he collaborated with Alessandro Cacciani in Sapienza, also University of Yale, University of Nice with Jean Arnaud, at the Institute for Astrophysics in Paris with Serge Kuchmi in Rio de Janeiro, and IRSOL. He's here a frequent guest at IRSOL, or maybe not so frequent, but we've seen him before. And so he's very interested in history and astronomy. So that became a fusion, and he's now a secretary of the IU Commission for History of Astronomy. And he's teaching history of astronomy at the University of Vatican, which is called Pontifical Athenaeum Regina Apostolorum. Excuse my Latin. And also he teaches this history of astronomy course at International Center for Relativistic Astronomy Network in Pescara. So today he will show us amazing history of solarigraphy. That's a new word for me. Along the centuries, how the idea of the sun become modern. So welcome.
Thank you very much, Svetlana, for the invitation and the possibility to have this talk. And when I'm sure that you see what I prepared, I will start to say. Let's say something about the title. Solarigraphy is a word that I discovered this year because in Prague, the Planetarium of Prague, they organized a meeting called Solarigraphy. And this meeting was...
Why this book?
This meeting was about the many things. I had to participate in remote because there was another meeting in honor of Gian Domenico Cassini, 400 years of birth. And so I could not split, but I sent them a contribution. So solarigraphy in Latin, in Italian, could be the drawing of the sun.
Mm-hmm. Yes, and graphical representation of the sun.
Exactly. And so I didn't limit it to graphics, but also to carving, because you see on the right side there is an image of the sun that I will present later. That I took here in Ascona, in the church of St. Peter and Paul, that will be inaugurated after the big restoration on 15th of November. So how the idea of the sun became modern, the summary of the talk will be how the sun became spherical. Was it always spherical or it was taught as a plane disk? Doesn't work.
It's here. Yes.
Oh.
In the middle, no, in the middle.
Yes. Okay, for supporting my hypothesis, I went to the Egyptian Museum of Turin because I wanted to prove that the representation of the sun were different, three-dimensional and two-dimensional. Well, The reason of linking to Egypt is not only because the pharaoh Akhenaton started to worship the sun as only one god, but mainly because in the eclipse that we saw together in different places in 2006 in Egypt or in the Libyan border, I had the occasion to see many temples of Egypt. We did study Egypt at school 3 times in Italy. So finally I could see the temples. And after seeing the eclipse and seeing the temples, I decided that this representation is not only the falcon Horus, but there is also something related with solar physics. And the relation with the solar physics is more evident here. This is a painting on stone, which is always in the Egyptian Museum in Turin, but it is a gift from Cairo, where you see the solar disk, 2 cobras below, and wings. So the idea that the solar disk with wings was the sun with the corona during an eclipse never left me for 20 years. Since that
I'm not sure if it's writing sound
in Egypt.
on the computer because microphone is off.
So you see these 2 things, the wings and the cobras. The cobras can be the protuberance, the prominences, and the wings, the wings.
Che bello!
Now I have to prove this hypothesis. The previous drawing is represented below.
I can
Just a second, because I muted myself.
Yeah.
And I think the sound is not.
Okay.
Yeah, I was using.
questions. Usually it is recorded.
No, Jimmy,
It's recorded from this computer.
I was out.
From this computer.
Yes, but if you have questions from abroad, they are also recorded. No? When you have
No,
a question.
We are trying to solve a problem of
Because
audio.
microphone is off.
Yes, but the Zoom. Okay. And then I can give you.
Do you hear me?
We can hear you, yes.
Okay, so
I can appoint you as a anyway.
I think you can put the audio there.
But then it will be
A sound, double sound.
I tell you, I did this before. Okay? Then it was 0 sound.
So if somebody is doing a question, you don't record it.
His voice is not recorded.
Yes, it is.
No, it's connected to your computer, not to mine.
It is as if somebody is doing a question from online.
They can see.
Is it not recorded?
No.
It arrives from.
Okay.
No,
Okay.
I don't think so. Anyway, so let's continue.
Anyway, this is an eclipse. It's 2009 eclipse. With the solar minimum going. And so the image of the wings explains what is the hypothesis of the corona. And the image of the prominences, the other eclipse is 2024. The big one, the big image on the right side is 2024 from United States, shows the red parts that are the cobras. More evidently, last month of July, we had a big prominences, and this could be a similar situation in one of the 30 solar eclipses that appeared in Egypt during the long Egyptian history. So why they didn't maybe one saw for the first time an eclipse with some red tint coming out, like I did with the binoculars, but they did not use optical instruments, but the colors they could see. And they firstly represented this thing. They translated this thing into a code, sacred code, which is the cobra, the wings, but they observed this thing. So it is possible that the first representation of the sun is related with solar eclipses. Moreover, in the third year of kingdom of Akhenaton, there was a total eclipse that probably changed the ideas to him, and he decided to change capital in Egypt, creating a new city, Akhetaton, instead of the other one. So this city has been studied, that is along the totality part of that eclipse in the fourth year of Akhenaton.
When was it, you said?
1400 and something before Christ. Now we are after Christ. The left one is a representation of Victor, of Jesus in catacombs, and his head has a radiating sun around it. And the other one is very famous because it is in the Basilica of St. Paul, outside the walls in Rome, in the central arch. So it is a representation of, solar representation of the one who defeated the death, Jesus. This is another idealized representation. And when I did present these two images, I was thinking to St. Francis of Assisi. Now is the 800th anniversary of this work, the Cantico di Frate Sole. It was composed between 1224 and 1226, the date of his death, and he is called also Cantico di Frate Sole because they mention that the sun brings the signification of God. So let's remain into a Franciscan context. You probably know this acronym, AIHS, which in Latin is Jesus Hominum Salvator, Jesus, Savior of the mankind. And this acronym is inserted into a radiating sun. It's the same that we found in the door of St. Peter and Paul, not the main one, one of the other one. There is another one, two other one door. The one facing east, northeast. So it is clear that this church, at least the work made for this door, were done under an influence of Franciscans, because this logo was invented by Saint Bernardine of Siena. The date of his birth and death are 1380 and 1444. In these two dates, there are two total eclipses in the center of Italy. I look the catalog of Marek Zawinski, a very good catalog of eclipses, in which he included also the chronicles about them. So was it possible that San Bernardine saw a total eclipse and afterwards he wanted to create this logo? When he was 6 years old, there was an eclipse very close to the place where he was born. An eclipse that is mentioned in Bologna, it was necessary at lunchtime, open the light, switch on the candles because they didn't see anything. So it was quite impressive indeed, this eclipse. This is an idea that San Bernardin saw it, but it is a matter of fact that he used this logo. It is represented to preach. He appeared with this logo in the preached about Jesus. So these representations are quite contemporary of San Bernardin. This one is in Madonna del Sasso, the left one in Orselina, near this place from where I am transmitting, and the other one is in Ascona, in the Church of Santa Maria della Misericordia, Collegio Papio. And both are, the one of Collegio Papio is probably just 100 years after or within 100 years of the death of San Bernardino. This looks more recent, but they are a particular sample of this preaching. In this image, the right one, San Bernardino is in the place from where it was used to preach, called Ambone, pulpito in Italian. No idea how to say in English it, but I had an occasion to see it working. It was like a balcony in the middle of the church, because without microphones, like now, they had to speak aloud, but they had to enter in this small box. So it is really evident. And now go to the history of astronomy. This is an image of the sun with the spots taken by Jean Tard in 1620. A similar image would have been taken by Kepler in 1607. So 3 years before the introduction of the telescope by Galileo, he had the possibility to see sunspots without a telescope. Now, in the title, I want to speak about how the idea of the spherical sun was formed, and the sunspots are objects that if you can follow for continuously, they help you to understand that there is a spherical thing that is rotating on itself. Another thing helpful is the limb darkening. Limb darkening is not moving, but you can guess that is a spherical situation. So how sunspots were visible at the beginning of the telescopic era or before? Or the same question about limb darkening. This is a book printed by the Lincei Academy on the sunspots. I had the possibility to see the original one in the Academy of Lincei last year, and so that's why the photo is three-dimensional, not exact. But you see with the eyes of experts that these are really big sunspots. Galileo, in the same book, says that the bigger one was visible to the naked eye.
Yeah, it must have been.
And it means that he knew how to see them with the naked eye. I would not say that he became blind because of that, not at all, because he was also clever. So he had many possibilities to see the sun without becoming blind. Anyway, a big sunspot visible to the naked eye can be a source of flares, and so of aurore. And aurore are aurora borealis is a name given by Galileo because he could see this phenomena looking toward north. This is the IRSOL telescope during the last eclipse. The eclipse was March 29, and in this moment there is a cloud over it. I took this photo because in this moment, or few seconds before or after, I could see the eclipse with naked eye because the cloud was perfectly filtering the sun. You can see probably from your screen that it is in this way. The thing in the second part of the image there would be an enlargement of the sun, but it came out. So you cannot see now. Why I put this image? Because we can estimate exactly the amount of arc minutes that the eclipse is in front of the moon is in front of the sun. So there is a minimum dimension under which the eye do not see anything. And this thing is exactly what it is necessary to discuss about the visibility of naked eye sunspots. Another big sunspot is this one last month of May. I don't remember the name of the region, the active region, but you see this is the full sun and this is the active region. This is not an image downloaded from the satellite, but it's an image produced in my room with a telescope, 90 degrees mirror inside the telescope is a finder scope, bigger than a finder scope, and projected on the wall, closing all the windows and leaving only the telescope out of the window. So the result is an image 1 meter in diameter. You can see very well the limb darkening and the spots. Going close to it, it is possible to see also the granulation. So this is an unexpected result because I didn't expect to see the granulation, but it was possible. So this kind of experiment is to reproduce what they did immediately after the introduction of the telescope. The most famous...
What you showed on the ceiling.
Yes, the most famous astronomer to do that, thanks to his publication, is Christoph Scheiner, a Jesuit father, that in 1630, so 20 years after, published a book dealing with the sun and sunspot observation and everything. These are details that I took from that kind of projection. So this was the big sunspot, AR 4199 probably was the number, or 4099, but I remember 99. And you see the faculae on the limb, very, very bright. So no tricks, the instrument was an instrument more developed than the one in 1630, because at that time did not exist the doublet, the chromatic aberration was strong, but they used to limitate, to diaphragm the telescope in order to avoid the chromatic problems. So faculae and spots were visible. I also observed some white light, let's say, experiences, flare maybe. In order to be sure about what I was going to say, I checked on Gong network and on the SDO the corresponding phenomena of that day. It was June 3. When the flare occurred, the limbs, the contrast is perfect to see some variation of luminosity. It is not a real telescope, it's the entrance of the subway in Rome, under a big tree, Platanus, and the light is coming through these leaves and going to the stairs. The images of the sun are formed. So my idea was it possible that in ancient time people observed already sunspots with these systems that are pretty occasional, they are casual? Well, there are Greek authors saying that something was already there, and there are studies dealing with these words. In particular, Aristotle explained exactly the pseudo-Aristotle in the Problemata, is a collection of problems made by the school of Aristotle. And they say the sun leaves show the eclipses, so they knew that. And is it possible that they could see some naked eye, some spot, at least with this instrument? I don't answer to this question.
But it's true. We could see it also.
Yes, we can
saw
see.
it on steps to IRSOL through bushes as well. When it was a bit bigger on partial.
Yeah. But the sunspots.
Sunspot.
The sunspots occasionally can be seen with this instrument. I saw also through the shades of the window. Now let's continue to see the representation of the sun moving back to the famous case of Stop, O Sun, Fermati, O Sole, that was belonging to the biblical tradition. Joshua with the hand to stop the sun and the moon there, to allow the Hebrews to combat against the people nearby. And since in the Bible was written "Stop, O sun," it was not possible that the sun was in the center. You know the history of the first condemnation of Galileo in 1615. This representation you can find in Santa Maria Maggiore is 5th century mosaic in Rome. And this is an image that we found in the Etruscan Museum in Vatican museums. The room is called Sala della Meridiana, the Meridian Hall, and you have the image of the sun in this way. So the first look at this image was a look to all other images. This is an image. Afterwards, I look better, and it is written, "This is the sun," by Father Kircher and Father Scheiner. And so I remained astonished looking this image. This is 1635, and you all know that in 1635 there was no H-alpha astronomy. So the image remained there, and I thought that it was a decoration made by the Cardinal Francesco Saverio de Zelada. He was a big cardinal of the last years of Pope Pius VI. And this, I am thinking if I said correctly this, well, it's the end of 1700. this was the pontificate. Pius VI followed Clemens XIV, who suppressed the Jesuits. It was a long history. Jesuits were the only one astronomers at that time in Catholic Church, but they were able to do many other things, and it came out this issue. So Cardinal de Zelada wrote the documents for the Pope to do this. Afterwards, the Cardinal took the observatory of the Jesuits, took care of it, the one in Collegio Romano. We are before Angelo Secchi. And so it is strange that he had to suppress them and to save their stuff, but it happened. So in his room, he created a meridian line through the window, and all the room was decorated by astronomical things. One of them is this, which is a sportello della finestra. I cannot translate. It's this one, sportello, and it was painted with the sun, with details on the sun. I found many years, many days later, many months later, the original one. And this is the Schema Corporis Solaris, brought about us, Padre Scheinero, Rome, anno 1635. The image of the body of the sun made by them. And so when you see this, you cannot imagine that it is difficult to imagine that he had this idea without H-alpha telescope, but the H-alpha technology came out 200 years and 250 years after that. So Father Kircher was one of the most knowledgeable men in his time, and he had the idea that the sun and the earth did work in the same way. Volcans and things below the volcans were connected, and so he influenced also the many artists, among which there is Bernini, who did the fountain in Piazza Navona, exactly thinking to this theory. Because you remember the fountain, there is an obelisk, and under the obelisk there is a 4 grottos connected, and these grottos were the place where the fire of the volcans could go from one place to another one. And the 4 things are the 4 continents. So the sun and the earth were similar, because this is published exactly in the Mundo Subterraneo, the underneath world, according to Father Kircher. So these white things that are here, putae lucis, wells of light, and the black things that are the maculae, are the most recurrent structure of the sun. Also, the sun is surrounded by what Angelo Secchi will call spicule, 200 years after. And what we are looking? We are looking at the interpretation of the sunspots as products of these volcans, but not real things. And this is an old problem. The sun, representing God, also for St. Francis, could not have spots. the spots could not be part of it. And so outgassing of something solved this problem, according to the Jesuits. But the wells of light are represented also in the body of the sun. We know that the faculae, name given by Galileo as maculae, also given by him in Latin, are visible only on the limbs. And what said Angelo Secchi 200 years later, in commenting this image, was that he had a great fantasy, but the great fantasy was supported by a great capability of modeling of Scheiner and Kircher, because they understood that the faculae rotated as well. So if they are on the lid, they should be also in the center of the sun. But what are the bright points?
There are also in between structures like this network magnetic fields.
Yes.
And maybe they saw this really network fields as bright points, you know?
Yes, it is wise not to say anything more, leaving to you the fantasy of interpreting
Granulation
by yourself. But yes, the idea of granulation is there. I thought also to the coronal mass ejection as seen in H alpha. You can see after a flare sometimes a small dark thing, but only in H alpha. And you can see white light flares. They were observing just before the onset of the Maunder minimum, but at the time of big naked eye sunspots. This is an enlarged images that I already discussed
And polar faculae are there also clear.
Yeah.
It's dominated in polar regions.
The separation of polar boreal northern and southern and the torrid thing is a separation that he made
It's correct, separation.
in full analogy with the Earth. Because the idea was also that their body followed the same. So it's something geocentric, even if they are studying the sun.
Well, there are triangles in those little eyes of volcans.
Triangles.
Yes.
This one.
Yeah.
This is A, and this in the downstairs with the H. A is a well of light.
Okay.
And now let's go to Santa Maria degli Angeli, where there is a meridian line bigger than the one of Cardinal Tezzevada. The cardinal was inspired to it. And we have the image of the sun ranging from 20 centimeters to 1 meter. This is a meridian line, pinhole-meridian line that allows us to see the sun in this dimension. The bigger one and the oldest one is in Florence. Santa Maria del Fiore, the
I know it.
lanterna of the dome, which was the biggest dome in the world, and it was the biggest church in the world.
Is it not the dome?
Santa Maria del Fiore was
No,
the
it's not.
bigger church in the world and as the tallest dome in the world when it was accomplished by Brunelleschi.
It's the main cathedral. Brunelleschi dome.
Yes.
It's the main cathedral. And when
After that,
I also was inside, but it's there inside this church or
sorry?
inside the church?
Yes, you can see the dome, and then a little lateral there is this
Yes,
meridian line, the
Transetto della Santa Croce on the left, that is the one going toward north, is the possibility
Like
to
the
see.
side chapel kind of, yeah?
Yes, it's a side.
Okay.
Is a wall, is the left arm of the gods, let's say. It's called chapel, but it's big,
Mhm.
as everything is big there.
Yeah,
So in the summer solstice, Paolo dal Pozzo Toscanelli, the correspondent of Christopher Columbus, the geographer, the astronomer, the magician, everything. It was a great,
magician.
yes, contemporary of Brunelleschi.
Yeah.
He was,
Brunelleschi was magician.
yeah, he was born in 1397, so he was
Mhm.
proved in
Mhm.
the previous century. Actually, he decided he decided to create this pinhole, 90-meter tall and 5 centimeter wide, producing that image. Now the problem is, can you see the sunspots from that thing?
Mhm.
In Santa Maria degli Angeli, which is 1/5 of that
Mhm.
instrument in Florence and has been created 2-3 centuries after, two centuries after, the sunspots are visible. So
They must.
they must be visible in
But it's
Florence.
projected on marble, so.
Here is on marble, but this black thing is white marble, so you can see easily.
There are lots of sunspots. on marble.
And so,
Okay.
this is another image that I made in my dark camera using a filter in front of the telescope to see, and you can see the dimension of the image with respect to me. So this big image is the same image that you can find in Florence in summer solstice. Without this kind of resolution, but the bigger spots should be visible. Now it happened that in that period, from 1475 to
It was Sporer minimum.
it was the Sporer minimum. So the sun did not show any spot.
Exactly.
And so the first spots were spotted by Kepler, but he didn't understand that it was a constant.
And Kepler was also 14 something. No.
1607 is the first news of Kepler, because he used the pinhole telescope to measure the eclipses. The eclipses are more easy to be measured, so but if there are sunspots, he could see them. So Florence was defeated by the sun that did hide and seek. In that moment, he hid the sunspots.
So then the Florence Cathedral was built in 16th century.
No, in 13, 12,
So, and they
13.
had already pinhole there.
No.
When did they build pinhole?
Well, Galileo says
Galileo.
explicitly that you have to go in a church finding a broken window.
The whole window.
If you have a pinhole, casual pinhole, you can see the sunspot. So obviously this property was already known to this genius Toscanelli that did not break any glass in Santa Maria del Fiore, but he created a bronzina cut with Swiss
knife.
a bronzina 5 centimeter wide, put there only in some days of the years, the days of the solstice, the summer solstice. In these days, the basilica can do this show again because the bronzina is still there, and they can open manage if they want. This year they didn't want for liturgical reason. I wrote to them to do that. So this is an enlargement of the 20 centimeter image of Santa Maria degli Angeli. That's why I use only this image now. And you have two limb darkening functions, the one of the pinhole upstairs and the one of the real image of the sun
is in Rome.
downstairs.
Yes. I just want to remember the names.
Yes. So here you have the different ramp a linear one upstairs and a smooth one downstairs. Can you recognize if this image has been made by a lens or by a simple pinhole? Yes, by looking at the histogram. Obviously, they didn't have an histogram at that time, but since the pinhole smears the details on the sun, you can see if the image is of the pinhole or not, if there are sunspots. Very different situation is the moon. The spots on the moon are always the same. But if you look at the moon in intermediate phases, it is very difficult to recognize the spots. You can recognize, but it is difficult to draw them. More easy is to compare plenilunar, full moon with full moons. And the first one to do something was William Gilbert in 1601. Gilbert made the first naked eye map of the moon, putting the spots that here are called continents, while the sea are what we call now the terre, using the Latin word. So this is the first attempt before the telescope to give a name to the spots. Here is a question: why the sunspots were not named? First, because they were not seen, but why the moonspot were not named? And this is another long history. Now let's come back to Santa Maria degli Angeli to do some measurement of the solar diameter. This is, the upper one is the image of winter, 1 meter and 10 centimeters, and the lower one is the image of summer, 20 centimeters. So you see very big images. In the winter one, unexpectedly, we found the sunspots very well, and a very high resolution. We can measure the position of the sun with a precision of 2 arc seconds. So here you have other cases of this kind of observations. The image on the yellow marble from Verona, and the image of the white marble of Greece, the Marmo Imezio, called also Marmo Cipollino, because of the structure when you cut it. And this black thing that you see on the white marble shows that the light passes below inside the marble, and is reflected from inside the marble. This enlarges the diameter, the perceived diameter of the image. Now you know that in recent years, in 2021, in Astrophysical Journal appeared a study based on measurements made in Bologna meridian line made by Gian Domenico Cassini. That was the reason why I didn't came in Prague, because I wanted to see the meridian line of Cassini and celebrate Cassini 400 years, 400th anniversary. So the first author is Tovar, and there are many other authors, said that the diameter of the sun measured in Bologna was not different from the diameter measured during the Maunder minimum and after the Maunder minimum, always in Bologna. So they are 80 years of data, the first 60 years in the Maunder minimum, and the second 20 years after the Maunder minimum. The measurement was made by hand. This is an example of measurement that I did on 26th of February this year on the meridian line and off the meridian line on the floor using pencil to sign the limit of the sun and the meter. You see that these measurements are not the same. If you go to the black marble, you have a smaller image. If you go to the white marble, you have a bigger image. But if you have a sky with a thin cloud, like not fog, because we don't know what is fog in Rome, but some veil very high in the sky. If you have that, you have an image which is slightly smaller, 1, 2, 3. It depends on the thickness of these clouds. And so in percentage, you have situation in which the image is smaller than the average one, let's say. This is an example of measurement out of the meridian. This is the bigger dimension of the image I could have this year. I could have even bigger, but some I had to open the church too early, and they didn't allow me to enter in this moment. But this is an image long 1 meter and 60 centimeters. It's very fast because the image runs literally. And so I put the meter on this stick in order to be quick to do the measurement. And to have the largest number of measure larger as possible. And this is the final result. They are more than 1,000 image points in and out of the meridian line. And we estimated the standard deviation, which is large when the image is very big and difficult to follow, which becomes smaller as the image becomes smaller. And we wanted also to know, I spoke to the plural, not like the popes, but we published this article in Universe this year with Andrea Brucato and Giulia Andreasi Bassi. We wanted to see if there was a systematic trend in the measurements, always thinking to the data analysis made in 2021 on the data taken in Bologna by Cassini 4 centuries ago. The method was the same. Maybe the pencil were different, but nothing more complicated than that method. This is an example made 2 years ago with Giulia, with a video on an image of a solar image moving for 2 seconds. So the image was almost there, and we analyzed the frame by frame using the inflection point of the image. And this is the variation of the image. Obviously, the center of the image is more stable than the limbs, and the limbs are more or less in phase. But the diameter has a variability in 2 seconds. So why showing this 100 images? Because it is meaningless to make the average of this image. No, the average you can do it, but saying that the error bar is decreasing with the inverse square root of the number of data is impossible. So if you have 1,000 of this or 1,000,000 of that, that is always the noise. What they did in the analysis of Bologna data, and the conclusion of this analysis that the solar diameter didn't change during the Mundo minimum and after. They did an average of things that are variating much more than that, because they are including not cloudy days, because they take them out, but veiled days. Veiled days are common. You don't see the veils. This is the situation, the experimental situation that we did in that experiment that we have seen before. So 2 seconds is a very small movement of this image. These are two places. We put the camera perpendicular to that and we analyzed frame by frame. This is an example of the intensity of the image obtained on 4 February during the meridian transit. The intensity is in arbitrary units, but you see that with veiled sky, it changes of this quantity. To the naked eye, you don't perceive that in that moment there are clouds, unless you see the movement. So the images changes their intensity, and it is possible that an observer caught this point or that point having a different diameter. So if you average them, you obtain something which is not even if you had 1,000 of that data, you never obtain the data of the diameter. So this is the comparison between the average and the single data in 1701 and 1702. This is what Bianchini did, Francesco Bianchini, the astronomer that built the meridian line in Santa Maria degli Angeli, what he did with this heliometer, the bigger one at that time available in the world. You see the error bar. This error bar is expressed in millimeters, but if you consider that the diameter is 1,000 of them, you have an error bar 1%. So you don't reach 0.6 arc seconds, never. These are the data that I took in the years 2016 to 2018 to 2024, and these are the dates of the year. So you see that I didn't upgrade very much what Bianchini did, because the variability is that one. And these are the best condition of measurement, because the resolution is 2 arc seconds. So this is the final slide in which I present the simulations of variation of the solar diameter of ranging from 1 arc second in 60 years, 60 years is the Maunder minimum duration, to 3 arc seconds. And the probability to observe something like that with this instrument is here represented. If you want more details, you can go to these 2 papers. The first one regarding the last consideration I made, and the last one is about the solar idea along the centuries. Thank you very much for your...
Thank you.
You're welcome.
Very interesting. Thank you so much. Questions, please. Maybe those who online first, because we have privilege here to ask questions during the visit also. Somebody online has questions? No, not yet. Okay, you're digesting still. And here, you have a question? Yes.
I was curious about what at some point you were saying that like already in the past, but also you said you saw the white light from flares, and I was curious what do you, I mean like in the what type of light did you see?
Okay, I used white light, so a normal telescope like optics that you find everywhere, projecting on the floor that the image. And I followed the active region when they were near the limb, because I was astonished about the clearness of the faculae. And so when there were flare in that region, I looked at the image to see if there was an enhancement of the faculae. And I try to be the most objective as possible, but in at least two cases, I have seen something which corresponded to an enlargement. And in one of them, I verified on SDO image in white light that there was some enhancement. In the other one, I didn't still, but it was 2 weeks ago, the region 42, 46, 46, what was the name. So white light, normal white light, not with observing with an eyepiece and a filter, no filter. The image is projected on the floor 1 meter far, so you don't need filters.
Another question?
This image that you showed with these small fires and that you said that it resembles H-alpha image before H-alpha technology became available. I was wondering, do you know if these people that observe this and then that make the image, Scheiner and Kircher, right? Did they have an idea of how big the sun is? I mean, do these images indicate some sort of size?
Well, Scheiner and Kircher were living more or less contemporary to Horrocks, who made the first observation of the transit of Venus in 1639. And Horrocks was looking that phenomenon basically for guessing the dimension of the sun with respect to Venus, and then a dimension of the sun itself, were the first attempts of having the astronomical units. The method for the astronomical units was the idea came from Halley, always on the transit of Venus, the forthcoming transit in 18th century. So I would say yes, that the sunspots were their dimension was fairly understood, at least a factor of 2 of uncertainty as at that time was the astronomical unit.
I have 2 questions. Why you assume that they give measurements on the marble? Why don't they put a white paper, white cloth, and then, because it's obvious for person that the reflection is better, they could use something white screen.
Yes. Well, the answer is the following. I went to French Guiana to observe the eclipse, the annular eclipse, in 2006, after the one in Egypt, because of in order to measure the solar diameter with Bale beads. And so in French Guiana, I wanted to find the best object to project the sun. So I said, paper, okay. Fabriano F3 paper, put the paper was filled by craters, small craters. So since you need to observe something very tiny, like the belly beads, if you have small craters in the paper, it's not good. So it's not good F3. So F2, F1, F4. I don't know what kind of
What is craters? I don't know.
craters are. Craters are the paper. If you look with the magnifier,
Structure.
is not
Yes.
flat.
Mhm. But it's bigger than marble.
I used also another thing taken in the kitchen for cutting the bread. It was white. I bought it in the supermarket. Also, it was not good for the projection. So in this moment, I realized that Francesco Bianchini was the astronomer, archaeologist, and the responsible of all the goods, archaeological goods in Rome, on behalf of the Pope, was aware that that kind of marble was the best one to do a perfect reflection. And so I had to say you were right to use this marble. Now, another thing, the problem of the internal reflection of the marble probably was not so big as the tiny veil of clouds.
Okay, then about this H-alpha image, I was wondering. So I looked up when the hydrogen was discovered. Basically, it's, they say different things. They say, in principle, it was known already early 1600. They didn't know it's hydrogen, but it was flammable gas. But in 1671, they say Robert Boyle discovered reaction between iron and acid and to produce the hydrogen, and then identify hydrogen like this. So I was thinking, okay, they could see sunspots through clouds, through smoke. Yeah, it's clear. We know it's from historical record. And they could also experiment, like if I see it through smoke, maybe I can burn something and I can see it through smoke this way or that way. Maybe at some point they burned something which contained hydrogen and they could see some more structures what they see that they drawn.
Yes, about burning a gas and obtaining colors, it can be done. There were many alchemics studies in this respect, but the start of spectroscopy, I would consider
it's
Newton, which is more or less the same time.
Yes.
Indeed, is 3 decades after the death observation of Scheiner and
also using prism. Yes, it's also infrared was discovered that put thermometer beyond red light.
Yes, in beginning of 1800.
And H-alpha is still visible light basically, so they could put prism and do pinhole through red part of the prism, for instance. I don't know.
Yes, some spectroheliography.
Yeah,
kind of.
Yes, it was already known in those times, and maybe they just experimented, and it's of course it's very artistic, but it's extremely close to what we see, like we say, H-alpha.
Yes, but since H-alpha, as you said, is visible light, probably they saw something more strong in visible light. Indeed, faculae.
No, I mean like in the red light. If you take a red light, then in the red light you could see better this, like by chance. Of course, it's very small range.
Well, filters, color filter were existent already.
Yeah.
Color, red, the vitrails of the churches.
Just I was thinking by chance they could have some view.
Yeah, but the faculae are not points, so probably the faculae are a network that is different from wells.
Yes.
But Angelo Secchi, I quoted his comments on it. There are some papers saved in the Gregorian University. He said he was an expert in in spectroscopy. So he said that they were really smart in having.
Even this 1520, first recorded observation of hydrogen by Paracelsus. It's like 100 years before. Yeah, I was thinking like not in spectra, but really like through gases, through smokes, because they, for me, it's like natural assumption. You see clouds, through some smokes or something. And they could take a candle, look through candle smoke. I don't know.
But the sun is very bright. That is the problem. You need a lot of gas to.
Yeah. What is projected? I mean, I don't know. Yes, it depends where you put it.
But Newton indeed did that.
Could be interesting. Yes. Yes. And another question is: do you know when they started to use pinholes for experiments?
The first one, which is known, is mentioned in Santa Hagia Sophia in Constantinople. But pinholes, as I said, it's mentioned by Aristotle. So they knew the principle. Camera obscura has been developed by Leonardo, by Della Porta. Always Leonardo in 1400.
Yeah, that's when Newton used it. He already used it like it was known very well. Yes, for his experiments in his shed. Even with plaque. What is called pandemic. Plague disease in England when he actually escaped from London to his village, to countryside house, and then he did this experiment. Yes, and he already used pinhole like it was like already scientific approach of those times. So it must have been.
The telescope used by Kepler is very interesting. The pinhole telescope, 4 meters wooden. There was a mask on it, and you could see the image there. And he put it out of the.
Yeah, but also, pinhole.
Ceiling.
Is in Persia, they observe stars from wells. Yeah, so they went down in the well. They could
Samarkand.
Yes.
There is the Ulugh-Beg instrument.
Exactly. Yes.
But this is 1420, not 1419. And he was killed afterwards. So he was a king, but he was killed.
Okay. Yeah, but Aristotle, you say, is mentioned already, so that's already far.
You can do many things with a pinhole and a mirror, a flat mirror.
No, very cool. Well, thanks a lot. Some more questions?
Thank you so much.
No?
Good work.
Okay, thanks a lot.
Yeah.
Okay, I stopped recording.